Yep. What day of the week was it? Tuesday. So we were looking at alkanes. So we've looked at the basics of organic chemistry. We've looked at how to structure alkanes. We looked at fractional distillation, and now we're going to have a look at cracking. So again, cracking isn't something that will be brand new. It will be something that was covered at GCSE, but we're just looking at it at the next level. Again, it's something that has to be covered at A level. So we're going to look at what supply and demand is, what cracking is, and the products that occur from cracking. Again, it'll just be a quick overview with just a little bit of extra information from GCSE. So basically, we have this demand for lower boiling points, so a shorter chain fractions, and it's greater than the proportion found in crude oil. So basically, we want more of this lower boiling point fractions than we can actually get from crude oil. So crude oil actually has lots and lots of longer chain fractions, so these fractions that have a really high boiling point, but these are in lower demand because they're less economically valuable and they're not that great and useful. So the lower boiling point ones are ones that have got this high demand, but they're rarer. We don't have as many. So we often have a shortage of these short chain fractions and we have a surplus of longer chain ones. So this is sort of where cracking comes into play. So cracking is a process that splits long chain alkanes into shorter chain alkanes, alkenes, and hydrogen. So this is sort of the process that we're looking at. So we've got a long chain alkane there. And what we do is we break it into that shorter chain of an alkanes and alkenes. So cracking has quite a few uses. So cracking can increase the amount of gasoline and other economically important fractions from when we do fractional distillation. It also increases branchings in chains, and that's actually a really important factor for petrol. So petrol, we want to have as many branch chains as possible in our alkanes that we use when we're having petrol. So cracking actually increases the amount of branches in the chain, so that really helps. It also produces alkenes. And alkenes are an important feedstock for chemicals, which is something we'll look at when we cover alkenes later. So there's two types of cracking. So we have thermal cracking and we have catalytic cracking. So we're going to look at thermal cracking first. So thermal cracking is a process that we use to split those long chain alkanes into shorter alkanes and alkenes. As you can probably imagine, thermal cracking involves heat. So here we go. We've got our displayed formula shows a long chain alkane. We have our R and R groups. They represent chains of singly bonded carbon atoms of unspecified length. So they're basically a residual group. They're just basically saying that actually on either end we've got all these extra carbons going on. So it's shown as a long chain. And so then what is thermal cracking? So what thermal cracking is, like I said, it involves heat and it involves actually temperatures of 700 to 12,000 Kelvin and actually a pressure of up to 7,000 kilopascals. And what happens in this is a carbon-carbon bond breaks and with one electron from the pair going into each carbon atom. So this carbon-carbon bond breaks. And like we were discussing before with those arrows, if I go back, we're showing those arrows as two separate arrows. So we're showing that the electrons are separating and they're single-headed arrows. So one electron is going to one carbon and one electron is going to the other. And we've got our free radicals, our free electrons there on each carbon. And so now we can see that it has now broken down. So then what happens is one of the hydrogen atoms moves from one fragment to the other. And what this does is it creates a shorter alkane and an alkene. So I'm going to replay that for you to see. We've got an open branch here. So what happens is hydrogen is attracted over to this carbon. This hydrogen moves from that chain to here. So now we've got a shorter alkane and now we've got an alkene. And the alkene can exist with that less hydrogen because then it double bonds the carbon together. So thermal cracking produces a larger proportion of alkenes, so usually ethene, but a lower proportion of branch-chained alkanes than catalytic cracking. So that's thermal cracking, uses heat, breaks the carbon bonds, electron goes to each carbon where that chain's been broken, a hydrogen comes over from one end of the chain to make an alkane and then an alkene. Thermal cracking, though, makes a larger proportion of alkenes to alkanes than catalytic cracking. So we're going to have a quick look now at what catalytic cracking is. So catalytic cracking, this is now a process used again to split long chain alkanes into shorter alkanes and alkenes. Catalytic cracking, as you can probably guess from the name, uses a catalyst to cause this reaction to occur. We use a catalyst called zeolite, and it means only slight pressure and relatively low temperatures are required. So thermal cracking was obviously really high temperature. So we're looking at 7 to 10,000 Kelvin, and then we're looking at about 7,000 kilopascals. Here, we only actually need around 700 Kelvin, so actually quite a low temperature. And zeolites contain large pores, so that's our catalyst, into which the alkane chain fits. So that's our zeolite crystal, and we've got those large pores on it, and the alkane chain will be able to fit into it. So what happens is the long alkane chain fits into the pores of the zeolite, and they're temporarily held in place. While they are there, they are then split into an alkane and a branched, they're split into an alkene and a branched alkane. So again, the long alkane comes in, held in place, they split, and they become a branched alkane and an alkene. Catalytic cracking produces more branched alkanes and arenes than thermal cracking. However, fewer alkane molecules are produced than thermal cracking. So catalytic cracking has several advantages over thermal cracking. So catalytic cracking produces a higher proportion of branched alkanes, and these burn a lot more easily than our straight chain alkanes. So they're really important in petrol. Catalytic cracking also uses lower temperature and pressure, so it's a lot cheaper. It produces a higher proportion of arenes, and these are valuable feedstock chemicals. However, unlike thermal cracking, catalytic cracking cannot be used on all fractions. So thermal cracking is great because we can use it on all fractions from fractional distillation, but catalytic cracking can't. So, bitumen, for example, the supply of this outstrips its demand, and we can't actually use that for catalytic cracking. So we also get some other products, from cracking. So alkenes, such as ethene, are always produced in cracking, and we can use them as feedstock in chemical industry, especially in production of plastics. But we also make arenes, such as benzene. Benzene is actually really important because we add it in small quantities to petrol, and we use this as a replacement for lead compounds. We replaced it for lead because obviously there's lots of concerns around lead and the use of lead in petrol and pollution in the air. But actually now we're starting to get a lot of health concerns around arenes as well. So we are starting to reduce the amount of arenes, such as benzene, that we use in petrol as well. So that was cracking. Let's have a quick look at alkanes and combustion. So we're going to look at what combustion is, understanding internal combustion engine, what a catalytic converter is, understand how fossil fuels can contaminate the atmosphere, and be able to name pollutant gases. So complete combustion. Again, it shouldn't be too much of a new concept. In excess oxygen, short chains of alkanes can undergo complete combustion. So if we have an alkane and oxygen, it can form carbon dioxide and water. So for example, propane and oxygen, we would get carbon dioxide and water. So the combustions of alkanes is a highly exothermic process, and this makes them really, really good fuels because they release a relatively large amount of energy per gram of fuel used. However, if oxygen is limited, then incomplete combustion will occur. So in this situation, we would have an alkane plus oxygen, and we might get carbon monoxide and water, or it might be an alkane and oxygen, and we might just get carbon and water. So for example, we could have propane and oxygen, and that would produce carbon monoxide and water, or propane and oxygen, and that could produce carbon and water. So the internal combustion engine for carbon, so alkanes with chain lengths of 5 to 10 carbon atoms are used as fuels in internal combustion engines. So these release carbon dioxide into the atmosphere. So we have nonane and oxygen, and they will release carbon dioxide into the atmosphere. So obviously because we're using them as a fuel, because of their exothermic properties. So though modern internal combustion engines are more efficient than in the past, incomplete combustion still occurs, so we can still be getting carbon monoxide being released into the atmosphere as well. So for example, nonane plus oxygen, we could get carbon monoxide and water. So the temperature in an internal combustion engine can actually reach over 2000 degrees Celsius. And in that, nitrogen and oxygen, which at normal temperatures don't react, can actually form, and they form to make nitrogen monoxide. So nitrogen plus oxygen forms nitrogen monoxide. Again, normal temperatures this doesn't occur, but when we're in temperatures of over 2000 degrees Celsius, this can occur. So nitrogen monoxide reacts further, forming nitrogen dioxide. So nitrogen monoxide joins with oxygen, and we can get nitrogen dioxide. And then again, nitrogen dioxide gas reacts with rainwater and more oxygen, and it forms nitric acid, and this contributes to acid rain. So this leads us to a catalytic converter. So a catalytic converter is used to transform pollutant gases in a car's exhaust into harmless gases. So how actually does one work? So what happens is our catalytic converters in a car, they contain either a ceramic or a metal honeycomb structure. And what this does is it's a honeycomb structure, as you can probably imagine, like in biology, it's this shape because it provides a large surface area. And this honeycomb structure that's either ceramic or metal is coated in a thin layer of catalytic material, which is often platinum, palladium, or rhodium. It's not always, but it's often one of those three. So here's an example of our car. Inside the exhaust, we have this catalytic converter. So we can see that honeycomb shaping. That's our outer casing, that's our honeycomb shape on the inside. It could be made of metal or ceramic, and then it's lined with the catalytic metal, so either platinum, palladium, or rhodium. So the main waste gases that occur from a car is carbon monoxide, nitrogen oxides, and unburned hydrocarbons. And what happens is these pass through the honeycomb structure and come into contact with the catalyst inside the exhaust. So if you pass through the structure and get in contact with the catalyst. In three-way catalytic converters, three reactions can take place. So what happens is carbon monoxide is oxidized to carbon dioxide. Nitrogen monoxide are reduced to nitrogen, and hydrocarbons are oxidized to carbon dioxide and water. Now, how well do these actually work? Well, catalytic converters can remove about 90% of harmful gases from a car's exhaust, which is actually really good. It's actually really useful. So that's only 10% entering the atmosphere, which is better than the 100%. So quick summary, nitrogen oxides, which are produced by combustion, tend to either be nitrogen monoxide or nitrogen dioxide, and they go through a reduction reaction, and this is catalyzed by platinum and rhodium. Oxidation reactions are catalyzed by platinum and palladium. Right, so sulfur contamination of fossil fuels. So sulfur is found as an impurity in crude oil and other fossil fuels. It burns in oxygen to form sulfur dioxide. So we've got sulfur and oxygen, and it forms sulfur dioxide. Sulfur dioxide could then further be oxidized to form sulfur trioxide. And both of these oxides dissolve in water and they form acidic solutions. So what is acid rain? So you can sort of see where all this is leading. So acid rain is caused by acidic non-metal oxides such as sulfur oxides and nitrogen oxides dissolving in rainwater. Rainwater is naturally acidic because carbon dioxide dissolves in it and it forms a weak carbonic acid. However, sulfur and nitrogen oxides form more acidic solutions, and these can damage trees and affect aquatic life in lakes and rivers. So removing sulfur dioxide pollution. So what do we do with this pollution? So sulfur dioxide emissions from vehicle fuels such as petrol and diesel are reduced by removing nearly all of the sulfur impurities from the fuel before we burn it. Oh. So what we do is we remove sulfur from coal before we burn it. It's not actually very practical. So instead what we do is the acidic sulfur oxides are removed from awake gases using a base such as calcium oxide. So actually when it gets to the waste stage, we remove the sulfur from the waste rather than actually from our base that we're using. So carbon dioxide in the atmosphere. So when we burn fossil fuels, again, carbon dioxide is released. And we're burning fossil fuels faster than we can make them, well, than the planet can make them. So it means that their combustion is leading to a net increase in the amount of atmospheric carbon dioxide we have. So it's been suggested that the increase of carbon dioxide and other greenhouse gases may be responsible for apparent changes to the climate. So we're going to have a quick overview now of greenhouse gases. So carbon dioxide, water vapor, and methane have all been described as the main 3 greenhouse gases. This is because they've been suggested as the gases that are responsible for most of the greenhouse effect. And we summarize the greenhouse effect as being a theory that suggests to explain apparent rises in the average temperature of the Earth, and it's increasing the amount of any of the greenhouse gases traps more heat energy from the sun in the Earth's atmosphere, raising the average temperature. So let's have a look at this next bit. And that. So, that was alkanes. We're now going to look at halogenoalkanes. That's not what I wanted. Here we go. Halogenoalkanes. So we've looked at alkanes, and now we're going to look at halogenoalkanes. So we're going to look at what they are, what prefix we use when naming them, or we've actually done quite a bit of that, so we'll just have a bit of a quick overview of that. What an R group is, and think about the differences between primary, secondary, and tertiary halogenoalkanes. So what is an halogenoalkane? They're similar to alkanes, but they have one or more hydrogen atoms and they're replaced by a halogen instead. So for example, you could have trichloromethane, chloropentafluorethane. So halogenoalkanes can contain more than one type of halogen. So for example, CFCs, so chlorofluorocarbons, and they contain both chlorine and fluorine. So some halogenoalkanes are useful themselves, but actually many are valuable as intermediates in the production of other molecules. So a prefix is added to the name of an alkane depending on what halogens are attached. We've done this before. Fluorine is fluoro, chlorine is chloro, bromine is bromo, and iodine is iodo. Prefixes again for our number of halogen atoms, nothing for one. If there's 2 of them, it'll be di, 3 of them tri, 4 tetra, and 5 penta. So another prefix is used to indicate how many atoms of each halogen is present. So numbers are used where necessary to indicate which carbon atoms each halogen is attached to. So type in the name, well, how would I type in the whole name of that in that? So for example, if we had one that looked like this, so we've got carbon with 4 chlorines around it, it would be tetra, chloro, and that would be how it would work. Why is it not moving? So primary, secondary, and tertiary. Actually, I'm just going to go through this now. So type in the name of the structure below. So it'd be tetra, chloro, methane. So that would be tetrachloromethane. Then we would have this. So it would be on the first carbon, our chlorine. So obviously it would be 1 chloro propane. I'm not going to go through them all because we did lots of these the other day. So we've got a chain of carbon atoms can be represented by R when drawing the structure. So it basically saves us time from actually just putting loads of R's on the page, which is really great. So we refer to this as an R group. So we have a primary halogenoalkanes, and these are ones that have one R group attached to the carbon linked to the halogen. We can have secondary halogenoalkanes, and these have two R groups, attached to a carbon linked to the halogen. And finally, you should probably imagine we have tertiary halogenoalkanes, and these have three R groups attached to the carbon linked to the halogen. So this one, for example, would be a secondary halogenoalkane because we've got an R group here and an R group here. But it's not branched, so it wouldn't be tertiary. Here we've got an R group here, an R group here, and an R group up the top. So that would be a tertiary halogenoalkane. Here the fluorine's at the end. So this would be a primary halogenoalkane because we've only got one R group then additional on the right-hand side. Our halogen is here on the first carbon. So again, because it's attached to the first carbon, it would still be a primary halogenoalkane because we would only put a primary, an R group on this side. This one, we've got bromine here. So it would actually only be a secondary halogenoalkane because we have a R group here and we'd have an R group here, and this branching doesn't come off this carbon where the halogen is, so therefore it would make it a secondary halogenoalkane, not a tertiary halogenoalkane. And then this one, we would actually be a primary halogenoalkane because that's branched off here, but the bromine's here, so it just comes off, so it'd be primary. And then finally, we've got our iodine here, we've got R group here, R group here, and R group there, so it'd be a tertiary halogenoalkane. So that's quick nomenclature for halogenoalkanes. So let's look at the synthesis of halogenoalkanes. So we're looking at how they're made, other products of chain reactions, and free radical substitution. So there's several ways we can make halogenoalkanes, and these can include free radical substitution of an alkane, or electrophilic addition of hydrogen or a halogen to an alkene. So what is free radical substitution? That's what we're going to look at first. So free radical substitution reaction involves highly reactive free radicals, and these are atoms or groups of atoms with unpaired electrons. So when exposed to UV light, a mix of chlorine and methane undergoes a free radical substitution reaction. There are three main steps in a free radical substitution reaction, and that is initiation, propagation, and then termination. So initiation. So when the UV light is absorbed by a chlorine molecule, providing it has enough energy to break the bond, that bond is broken and one electron goes to each chlorine, and this creates two free radicals, and this is homolytic fission. So we've created two free radicals here. So UV is strong enough to break that bond between the chlorine. One electron goes to each chlorine, and it makes two chlorine free radicals. So many chlorine molecules are split by homolytic fission. So this initiation step leads to a rapid increase in the number of chlorine free radicals we have at hand. So we get something like this. So propagation. As a chlorine radical is able to react with a methane molecule, and it removes a hydrogen to create a methyl radical and hydrogen chloride. So here we've got, why is it paused? Let's go back to the beginning. So we've got a chlorine free radical. We've got our methane, reacts with the hydrogen. So we get chlorine and hydrogen bond in, and then we get a methyl radical. So we've got methyl radical here, and we've got HCl there. So then propagation 2. A methyl radical then reacts with a chlorine molecule, and this creates another chlorine radical and a chloromethane. During propagation, the total number of free radicals remains the same. It's just that we're forming other things at the same time. So again, I'll go through this. The methyl radical reacts with a chlorine molecule. The chlorine molecule bond's broken, we get a chlorine radical, and we get chloromethane forming. Then termination. In termination step of a free radical substitution reaction, the total number of free radicals decrease. So for example, a chlorine and methyl radical can react to form chloromethane. Another type of termination step occurs when two chlorine radicals react to form a chlorine molecule. Or termination 3. A third type of termination step occurs when two methyl radicals react and they form ethane. So free radical substitution, quick summary. Free radical substitution is a type of chain reaction. The reactions in the propagation steps ensure there is a constant supply of free radicals, so it is self-sustaining. So we go through initiation, propagation 1, propagation 2, and we have termination 1, 2, and 3. So if an alkane is more than 2 carbons in length, then any of the hydrogen atoms may be substituted, and this can lead to a mixture of different isomers. So we could have 1 chloropropane, 2 chloropropane. So the mixture of products is actually difficult to separate. And this is one reason why chain reactions are not a good method of preparing halogenoalkanes, because we can get a mix of isomers. So some chloromethane molecules that we form during that free radical substitution between methane and chlorine can actually undergo a further substitution, and they can form dichloromethane. And this further substitution can occur until all hydrogens are substituted. And this further substitutes chloroalkanes are impurities that must be removed. And the amount of these molecules can actually be decreased by reducing the proportion of chlorine that we add into the mixture. So nucleophilic substitution reactions. I think this is the right one that I want. Yes, it is. So sticking on halogenoalkanes now, we're going to look at polar bonds and nucleophiles. Think about nucleophilic substitution reactions involving halogenoalkanes and learn about the rate of nucleophilic substitution. So the carbon-halogen bond in halogenoalkanes is polar. And why it's polar is because all halogens are more electronegative than carbon. So fluorine's more electronegative than carbon, so is chlorine, bromine, and iodine. So the polar bond means that our carbon has a small positive charge. And this small positive charge is able to attract substances with a lone pair of electrons. These substances with a lone pair of electrons are nucleophiles, and these mean nucleus loving, so nucleus positive charge loving. So examples of these include ammonia, cyanide, and hydroxide. So nucleophiles attack the carbon of a carbon-halogen bond. Because the electron pair of a nucleophile is attracted towards a small positive charge on the carbon, then the electrons in the carbon-halogen bond are repelled as the nucleophile approaches the carbon atom. The nucleophile bonds to the carbon, and the carbon-halogen bond breaks. The two electrons move to the halogen, forming a halide ion. And the halide is substituted, so this is a nucleophilic substitution reaction. So nucleophilic substitution reactions involve halogenoalkanes, and they're important because of their production of other useful molecules. We're going to look at reaction of halogenoalkanes with OH-. So halogenoalkanes react with aqueous solutions of sodium hydroxide or potassium hydroxide when warmed. So the negatively charged hydroxide ion is attracted to the small positive charge on the carbon atom. Again, our hydroxide ion is a nucleophile. The carbon is positively charged, so it's going to be attracted there. The electron pair on the hydroxide ion donate into the carbon atom. So then this increased electron density on the carbon causes the electrons in the carbon-bromine bond to be repelled to the bromine. So that happens. And then this results in the formation of a covalent bond between the carbon and oxygen, and this creates an alcohol, and the carbon-bromine bond is broken simultaneously, and it forms a bromine ion. And this process is called hydrolysis. And that's because we've had that addition of water in there. So now we're going to look at what happens if you added solutions with cyanide in. So the negatively charged cyanide ion, again, is attracted to the small positive charge on the carbon atom because the cyanide, again, is a nucleophile. In a similar way, the electron pair on the cyanide ion donates into the carbon atom. The increased electron density of the carbon causes the electrons in the carbon-bromine bond to be repelled to the bromine, and therefore this results in the formation of a covalent bond between the carbon and the CN group, forming a nitrile, and the carbon-bromine bond is simultaneously broken and it forms a bromine ion. And then we're going to look at the reaction of halogenoalkanes with excess ammonia when warmed in a sealed container. Probably notice it's going to be pretty much the same. So our lone pair of the ammonia molecule, nucleophile again, is attracted to the small positive charge on the carbon atom. The electron pair on the ammonia is donated to the carbon atom. The increased electron density in the carbon causes electrons in the carbon-bromine bond to be repelled to the bromine. This results in the formation, again, of a covalent bond between the carbon and the nitrogen, and the carbon-bromine bond is simultaneously broken, forming a bromide ion. Now, the lone pair of another ammonia molecule attacks one of the hydrogens attached to the nitrogen. This results in the pair of electrons in the nitrogen-hydrogen bond moving on to the nitrogen. This results in the formation of an amine and ammonium bromide. Amines themselves are nucleophiles, so may attack and further substitute the halogenoalkane. So the rate of nucleophilic substitution reaction depends on the strength of the carbon-halogen bond rather than the degree of polarization in the bond. So as we see, carbon-fluorine is the highest, the lowest is carbon and iodine. So carbon and iodine is the weakest and so most readily undergoes nucleophilic substitution. The rate of reactions involving iodoalkanes are the highest. So we're going to look at elimination reactions now. So in a reaction with a strong base, our halogenoalkanes will undergo not only nucleophilic substitution, but they also undergo something called an elimination reaction, and these form alkenes and water. So in this situation, our hydroxide acts as both a base and a nucleophile. So when acting as a base, the hydroxide ion removes the hydrogen ion from the halogenoalkane, which also results in the formation of a halide ion. The reaction between a halogenoalkane and a strong base usually results in the formation of a mixture of substitution and elimination products. So we're going to look at that process now. So step 1. The lone pair on the base, the hydroxide ion, attacks one of the hydrogen atoms on a carbon adjacent to the carbon to which the halogen is attached. So there we go there, that's our example. So then the electrons in the carbon-hydrogen bond are pushed to the carbon-carbon double bond, carbon-carbon bond, making it into a double bond. And then the electrons in the carbon-chlorine bond are repelled onto the chlorine, and thus we've got a chloride ion. And it's a chlorine free radical. So the resulting products of reaction are an alkene, a chloride ion, and a water molecule. So if our carbon chain is 4 or more carbons in length and our halogen is not attached to a terminal carbon, we can actually get a mixture of positional isomers being formed. So attack A, attack B, so we could get butene, but1ene, we could get loads of different things. The conditions for the reaction that favour substitution or elimination are actually really different. So it depends on the base strength. So the stronger the base you use, the more elimination is favoured. So sodium hydroxide in an aqueous solution contains hydroxide ions, but when dissolved in ethanol, CH3CH2O- is also present, which is actually a stronger base. Therefore, elimination is favoured by sodium hydroxide in ethanolic solution, and substitution is favoured by sodium hydroxide in aqueous solution. Temperature. Elimination is favoured at hotter temperatures, whereas substitution is favoured by warm conditions. So primary halogenoalkanes favour substitution, whereas tertiary halogenoalkanes favour elimination. So here's our primary, secondary and tertiary halogenoalkanes, and to the left substitution is more likely. To the right, elimination is more likely. So what we're going to do now is we're going to have a look at alkenes. Quick overview of nomenclature again. No, we did this the other day, but just a quick overview for alkenes. So alkenes are a homologous series of hydrocarbons, and they have the general formula of CN, H2N, and their names end in -ene. Alkenes contain a carbon-carbon double bond, and they are unsaturated. So we have ethene, propene, butene, pentene, and hexene. Alkenes with 4 or more carbon atoms are able to display positional isomerism, and this is because the carbon-carbon double bond may appear between different carbon atoms. If there are 2 or more possible positions for the double bond, a number is used before the ene to indicate the first carbon involved. So for example, but1ene, but2ene. We looked at these the other day, so let's look at bonding in ethene. So what is the nature of double bonds in alkenes? So our carbon-carbon double bond in an alkene consists of 2 different types of bonds, and these are a result of the overlap of different atomic orbitals. So the first type of bond that results from the end-to-end overlap of orbitals as occurs in a single carbon-carbon bond, and this is a sigma bond, and this is the strongest type of covalent bond. So that is our sigma bond, the first bond that occurs. The second bond results from the sideways overlap of atomic orbitals above and below the sigma bond. This is the pi bond, and its electron density is less than that of a sigma bond. So again, that's our sigma bond. We've got this overlap at the top and bottom, and that is our pi bond, and its electron density is less than that of a sigma bond. The pi bond prevents rotation about the double bond, and it means all atoms lie in the same plane. The shape of ethane is planar, with the bonds around each carbon at an angle of 120 degrees to each other. So rotation around the double bond in alkenes is restricted, and that's because of the presence of that pi bond, and this can lead to something we talked about before called EZ stereoisomerism. So we have E-pent2-ene and Z-pent2-ene. So the 2 EZ stereoisomers have exactly the same structure, but their arrangement of their atoms in space is different. The Z isomers have the 2 higher atomic number atoms, so for example carbon in this situation, attached on the same side of the molecule, and the E isomers have the higher atomic number atoms diagonally opposite each other in this molecule. So what we're going to look at now is addition reactions in alkenes. So double bonds and electrophiles. So alkenes are more reactive than alkanes, and that's because the bond enthalpy of the pi bond is significantly lower than the bond enthalpy of carbon-carbon single bonds and double bonds. The double bond of an alkene is an area of high electron density, and therefore an area of high negative charge. The negative charge of a double bond may be attacked by electron-deficient species which will accept a lone pair of electrons. These species have either a full positive charge or a slight positive charge on one or more of their atoms. They are called electrophiles, and that means they are electron-loving. Alkenes undergo addition reactions when they are attacked by electrophiles, and this is called electrophilic addition. So electrophilic addition mechanism 1. So in the first stage of electrophilic addition, the positive charge on the electrophile is attracted to the electron density in the double bond. So that's our electrophile, which is to the double bond. As the electrophile approaches a double bond, electrons in the AB bond are repelled towards B. The pi bond breaks and A bonds to the carbon, forming a carbon cation, an ion with a positively charged carbon atom, and the two electrons in the AB bond move to B, forming a B- ion. In the second stage of electrophilic addition, the B- ion acts as a nucleophile, and in this situation it attacks the carbocation. And the lone pair of electrons on the B ion are attracted towards the positively charged carbon in the carbon cation, causing B to bond to it. So what is hydrogenation? So hydrogen can be added to the carbon-carbon double bond using a nickel catalyst, and this is called hydrogenation. So vegetable oils are unsaturated and may be hydrogenated to make margarine, which has a higher melting point. So as well as a nickel catalyst, this requires a temperature of 200 degrees Celsius and a pressure of 1000 kilopascals. So how can we test for alkenes? So the presence of unsaturation, so a carbon-carbon double bond, can be detected using bromine water, a red-orange coloured solution of bromine. So a few drops of bromine water are added to the test liquid and we shake it. If there is a carbon-carbon double bond present, the bromine adds across it and the solution turns colourless. If not, it would stay the same colour. A simple equation for a bromine water test with ethene is ethene plus bromine plus water. However, because water is present in such a large amount, a water molecule, which has a lone pair, adds to one of the carbon atoms, followed by the loss of the hydrogen ion. The major product of the test is not 1,2-dibromoethane, but actually 2-bromoethane-1-ol, so forming an alcohol. So electrophilic addition reactions of ethene. So electrophilic addition reactions are important reactions, and in these, atoms are added across a double bond, such as in alkenes. So reaction of ethene with bromine. So alkenes react with bromine to form bromoalkanes by electrophilic addition. The bromine molecule has no permanent polarity, but as it nears the alkene, the electron density in the bromine-bromine bond is repelled towards the bromine atom furthest away from the alkene. When this happens, this results in a temporary dipole occurring. The electron density in the double bond in ethene attacks the slight positive charge of the closest bromine atom, which acts as an electrophile. And in turn, this causes our bromine molecule to split by heterolytic fission. A bond forms between one of the carbon atoms and the closest bromine atom, and this forms a carbocation and a bromide ion. The lone pair on the bromide ion attacks the carbocation and bonds to the other carbon atom and forms a 1,2-dibromoethane, a bromoalkane. So we can also react ethene with hydrogen bromide. So alkanes can react with hydrogen bromide. Very similar. Hydrogen bromide, again, it's a polar molecule. So the electron density of a double bond in ethene attacks a slightly positive charge from a hydrogen atom, and thus acts as an electrophile. A bond forms between one of the carbon atoms and the hydrogen atom, and that forms a carbocation and a bromide ion. The lone pair of the bromide ion attacks the carbocation, bonding to the other carbon atom and forms bromoethane, a bromoalkane. As you can probably guess, reaction of ethene with sulfuric acid, pretty much the same thing's going to happen. Sulfuric acid's polar, so the electron density in the double bond in ethene, again, is going to attack the slightly positive charge on one of the hydrogen atoms, which acts as an electrophile. Because of this, a bond forms between one of the carbon atoms and the hydrogen, and then that forms a carbocation and hydrogen sulfate ion. So then that lone pair on the oxygen of the OSO3H ion attacks the carbocation, bonding to the other carbon atom and forming ethyl hydrogen sulfate. If the ethyl hydrogen sulfate is warmed with water, we can actually form ethanol, and the sulfuric acid is regenerated. So when an electrophile, like hydrogen bromide, attacks an alkene with 3 or more carbon atoms, a mix of products is formed, and this is because these alkenes are unsymmetrical. So we could get a minor product of 1 bromopropane or a major product of 2 bromopropane. Unequal amounts of each of these products are formed, and that's due to the relative stabilities of the carbocation intermediaries. So a chain of carbon atoms can be represented again by an R group when drawing organic structures. So in this situation, this would be an alkyl group. So we can have primary carbocations have 1 alkyl group attached to the positively charged carbon. Secondary have 2 alkyl groups attached to the positively charged carbon. And tertiary have 3 alkyl groups attached to the positively charged carbon. The stability of carbocations increases as the number of alkyl groups on the positively charged carbon atom increases. The stability increases because the alkyl groups contain a greater electron density than hydrogen atoms, and this density is attracted towards and reduces the positive charge on the carbon atom, which has a stabilizing effect. Okay, so I'm going to leave it there for today. I've lost my background, so that doesn't help. So